In this lecture, we look at the algebra and geometry of complex numbers. Mathematicians began to recognize the value of complex numbers sometime back in the Renaissance period, in the 15th and 16th centuries, but it was not until there was a geometric interpretation of complex numbers that people began to feel comfortable with them. We may view the complex numbers as lying in the Cartesian plane. Let the traditional x-axis represent the real numbers, and the traditional y-axis represent numbers of the form y times I. We equate a complex number x plus y times I with the point x comma y. So the imaginary numbers involving y times I are perpendicular to the set of real numbers. Here, the horizontal axis across the bottom of the diagram is the real axis. It includes numbers like -1, 1, 2, and 6. And the vertical axis going up the page includes complex, purely imaginary numbers like I, 2i, and 5i. Numbers like 6 plus 5i up to the right are where we would traditionally have 6, 5. The process of changing a plus bi into the point ab can be traced to the mathematician Argand around 1800, and so this is sometimes called the Argand diagram. In the Argand diagram, the complex number a plus bi is equated with the point ab in the Cartesian plane. So 6 plus 5i in the upper right can be graphed to the point 6, 5. The ordinary Cartesian plane then becomes a plane of complex numbers. In fact, in some graphing calculators, an ordered pair like 6, 5, if you try to square it, the calculator will treat it as 6 plus 5i and assume it's a complex number. Here's the Argand diagram again off of Wikipedia. We'll equate I as 0 plus 1i with the point 0, 1 going up, and the number 1 is just 1 plus 0i going to the right, equated with the point 1, 0, and in general, a plus bi is equated with a plus b. So 2, 1 would represent the number 2 plus I, and square root of 3 plus I over 2, which we'll run into later, would be equated with the point square root of 3 over 2, comma 1 over 2. So the horizontal axis is the real axis, and the vertical axis is the imaginary axis. The complex numbers have a natural addition, subtraction, and multiplication. We add and subtract complex numbers just like we would polynomials, keeping up with the real and imaginary parts. For example, if we add 3 plus 4i to 7 plus 11i, we simply collect like terms and get 10 plus 15i. And if we subtract, again, we collect like terms. 3 minus 7 is minus 4. 4i minus 11i is minus 7i. We multiply complex numbers just as we would with polynomials, except that we need to remember that I squared is minus 1. For example, if you multiply these two polynomials, if you expand them out, you get this expression. So if instead we multiply 3 plus 4i times 7 plus 11i, the first step would be to get the same expression. You expand as you normally would. But remember that I squared is minus 1, so 44i squared is minus 44. And then now that I've written 44i squared is minus 44, I can collect like terms, the 21 and the minus 44, and get minus 23 plus 61i. Adding, subtracting, and multiplying complex numbers is all very easy and straightforward. We would like our complex number to be written in Cartesian form, a plus bi, so when we do division, there's a little bit of a twist here, something extra we have to think about. Notice that if a plus bi is my complex number, then when we multiply it by its conjugate, because we have a product of sum and differences, then we end up getting a squared minus b squared I squared, which is the same as a squared plus b squared. So if we're dividing by z, we might view 1 over z as z bar over z bar over z bar, multiplying by that conjugate, and we get this expression. Computationally, the point here is that anytime we have a fraction involving a complex number, we multiply numerator and denominator by z bar and simplify. For example, suppose we have 3 plus 4i divided by 7 minus 11i. We will multiply top and bottom in this fraction by 7 plus 11i, the conjugate, and when we do that, simplifying the top and the bottom, we end up getting a real number in the denominator. And so we can express this in real parts minus 23 over 170 plus I times that imaginary part 61 over 170. This process, multiplying the numerator and denominator of a fraction by the conjugate of the denominator, is called rationalizing the denominator. Let's do some problems. We're going to do all four of these fractions. In the first case, 3 plus 2i over 7 minus 3i, we multiply top and bottom by 7 plus 3i by the conjugate, and then we expand out both the numerator and the denominator. And if we want the real and imaginary parts, we can break them up into 15/58 plus 23/58i. If we divide by 3 plus I, it's the same as multiplying top and bottom by 3 minus I. Do the algebra. So my answer is 3/2 minus 1/2 I. Again, if we're dividing 2 by 1 plus I, multiply top and bottom by 1 minus I. Do the algebra. Simplify. Even 1 divided by I, if you multiply top and bottom by the conjugate, which is minus I, and do the algebra, you get minus I over 1, which is just minus I. We want to be ready to use complex numbers when factoring polynomials or solving polynomial equations. For example, let's factor this polynomial. Since this is a cubic polynomial and we don't want to use the cubic formula, there is one, but trust me, it's quite messy, then we need to find a zero. We could try some numbers, that'll be some techniques in the next lectures, and discover by trial and error that f of 2 is 0. Or we could graph this polynomial on a graphing calculator or on a computer program like Sage and see that x equals 2 is a 0. Since f of 2 is 0, and you might check that, then x minus 2 should be a factor. So let's divide x minus 2 into this cubic using synthetic division, and I get an answer of x squared plus 9. So this cubic polynomial factors into x minus 2 times x squared plus 9. Since x squared plus 9 equals 0, has zeros x plus equal to plus or minus 3i, then x squared plus 9 factors into x minus 3i times x plus 3i. So the whole thing factors into x minus 2 times x minus 3i times x plus 3i. Here's another problem. We can factor the polynomial x cubed minus 8 and find all solutions. We know then one solution is 2 because 2 cubed is 8. Since f of 2 is 0, then x minus 2 again is a factor, and so we can divide x cubed minus 8 by x minus 2 and get a quadratic x squared plus 2x plus 4. The solutions to this equation x cubed minus 8 equals 0 are then the solution to this equation x minus 2 times this quadratic is equal to 0. By the quadratic formula, the solution to the quadratic equation x squared plus 2x plus 4 equals 0 are this: 1/2 times minus 2 plus or minus 2 square root of 3i, or, after simplifying, minus 1 plus or minus the square root of 3 times I. This implies that my quadratic factors into these pieces. If minus 1 plus root 3 times I is a 0, then x minus that is a factor. So my two zeros for the quadratic give me these factors. A 0c for a quadratic gives me a factor x minus c. And so I can factor the cubic in this way, into three pieces. This is the full set of solutions to the equation x equals 2, x equals minus 1 plus root 3i, and the conjugate x equals minus 1 minus root 3i. One more problem. Let's factor completely x to the 6 minus 1. The fundamental theorem of algebra tells us that x to the 6 minus 1 has 6 zeros, and therefore factors into 6 linear pieces. One way to factor x to the 6 minus 1 is to view this polynomial as a difference of squares. Think of x to the 6 minus 1 as x cubed plus 1 times x cubed minus 1, recognizing that x to the 6 is x cubed squared. Then to further factor x cubed minus 1, notice that x equals 1 is surely a 0. And after synthetic division, we can see that x cubed minus 1 factors into x minus 1 times x squared plus x plus 1. You might do the synthetic division on your own. In a similar way, minus 1 is a 0 of the other part of x cubed plus 1, And so x plus 1 should be a factor. Divide x cubed plus 1 by x plus 1 and get x squared minus x plus 1. And so we now have that x to the 6 minus 1 factors into those two degree 3 polynomials, and that we've broken those degree 3 polynomials up into a linear term like x plus 1 and a quadratic like x squared minus x plus 1. And we factor this degree 6 polynomial into these 4 factors, 2 of them quadratic. We still have to factor the quadratics. So here's x to the 6 minus 1 at this point. We've not yet done. We need to factor those quadratics, x squared minus x plus 1 and x squared plus x plus 1. And in an early example, we factored these already using the quadratic formula. And we found that x squared plus x plus 1 is this, and x squared minus x plus 1 was that. So the whole thing, x to the 6 minus 1, factors into those 4 terms, but the quadratics factor themselves in the linear pieces, and there are 6 linear factors of x to the 6 minus 1. I've gone through this somewhat rapidly. You might go back and see if you can verify each of the steps. Notice that in this last example, relying on complex numbers and the formula for a difference of squares, we were able to break the 6th-degree polynomial x to the 6 minus 1 into 6 linear terms, as promised by the fundamental theorem of algebra. In the next presentation, we return to studying the zeros of polynomials.